Hello everyone, my name's Dakota Lambert, and today I'd like to talk to you about learning tier-based strictly local languages in an online manner via different interpretations of grammars. To start with, we'll discuss word models and constraints over them. A word model is just a sequence of domain elements and connections between them. For a local dependency or strictly local constraint, all you need is a connection from each node to its immediate successor. An instance of this is the requirement that all words follow a CV syllable pattern. If you encounter a word like that shown on the left, CVC, CV, the CC connection in the middle represents a violation of this constraint. On the other hand, for a long-distance dependency or a strictly piecewise constraint, you use not just a connection to the immediate successor, but also to all of the other successors. For instance, we could represent Finnish vowel harmony this way, in which the set of round vowels is partitioned such that words never contain both a front and back version of a round vowel. So this herno word is not a valid Finnish word. The back round vowel at the end is forbidden by the front round vowel near the beginning. This connection between them represents the violation of that constraint. Sometimes you'll see the word boundaries marked with an additional domain element on the left and right, marked with the start fish and end fish respectively. These are not useful in long distance dependencies because, well, the one always precedes everything and the other always follows everything. However, they do come up in the local dependencies. However, another type of long distance representation is just ignoring the symbols that don't matter. This is tier-based strictly local. In this case, you have what looks like a local model with some other nodes scattered about, the domain elements that aren't connected, that aren't relevant. Here again we see the Finnish vowel harmony pattern, where the consonants have been ignored and only the round vowels are retained in the connections. Here we see the same connection that caused the violation before, so it represents the same pattern. The learning problem, in general, is given some finite amount of data, be that positive data, representing words in the target language, or negative data, representing words marked as not being in the language. The goal is to make the right generalizations to learn the target constraints. There are some restrictions one could put on this. In 1967, Gold proposed several learning frameworks, one of which that we're particularly interested in is learning in the limit from positive data, often abbreviated to ILPD. In this framework, no attention is given to negative data, and as Charles Yang pointed out in 2015, this can be a common assumption with human learners, and you can still learn negative constraints with only positive data. Another property of the ILPD framework is that it requires exact convergence to the target grammar, unlike, say, a PAC framework, which only requires correctness probabilistically. The requirement here, then, is that every sufficiently large text must contain a characteristic sample of the language you're trying to learn. Another type of restriction is online learning, where there's a constant bound on memory requirements. A benefit of online learning is that you can adjust your hypothesis without having to review all prior data. This contrasts with a batch learning approach, where adjusting the hypothesis requires constructing a new batch containing all the previous data as well as the new data that you'd like to account for. The requirement here is that all words can be parsed into finitely many categories of informational content. A general online learner for the In the Limit from Positive Data framework is Jeff Hines' string extension learners from 2010. Here we define a function phi of a grammar G and a word W. Now here W could be either a word over some finite alphabet sigma or a special symbol. Here I just use the circled circ to represent no data appearing at that point in time. So if you get the no data word, then you just return the original grammar as is. You have no reason to change it. Otherwise, you need to extract the informational content from the word, that's the function f here, and insert that content into the grammar to return that, and that is the O+ operator. In order to learn strictly local or strictly piecewise constraints, you can use this. Here the grammar is a set of permitted k-factors, that is, connected components of the word model of width up to k. F, the information extraction function, just gives you the k-factors from the word. And O+ is set union, taking the set of k-factors, unioning it into the grammar. The challenge for learning tier-based strictly local constraints is that what the k-factors are depends on what the tier of salient symbols is. So deciding which symbols are salient is important. Some examples of tier-based strictly local constraints and their tiers are on this slide. For instance, there's the liquid dissimilation of Latin, whose tier alphabet is the liquids, L and R, as well as the non-coronals, which I've represented just as K. The forbidden factors, that is, the complement of the set of permitted factors, is LL and RR. That is, you can't have like liquids adjacent without one of these non-coronals intervening. Another sort of TSL constraint is the one-stress constraint, the requirement that exactly one syllable with primary stress occur in any given word. In this case, the tier alphabet is the set of primary stress syllables. And what's forbidden? Well, the empty word. That is, you can't have a left end marker immediately followed by a right end marker on the tier. And what does this require is that you have at least one symbol of primary stress in the word. But also, you can't have two primary stress syllables adjacent to one another on the tier. And since the tier consists only of primary stress syllables, that's equivalent to saying you can't have two primary stress syllables in the word. At most one. At least one and at most one combine to give us exactly one stress. And as discussed, the Finnish vowel harmony operates over the tier of round vowels, and you can't have a front vowel followed by a back vowel, or a back vowel followed by a front vowel on this tier. Prior methods for learning tier-based strictly local constraints and their tiers include one by Jardine and Hines in 2016, where you extract subsequences as well as their interveners. They refer to these as paths. I will call them augmented subsequences. So, for instance, the word talo contains TA with no interveners, TL intervened by A, and TO intervened by A and L. AL with no interveners, AO intervened by L, and LO with no interveners. Once you've found all of these augmented subsequences for every word in the text, how do you find the tier? Well, first you have to find the free elements. It is those that are unrestricted in their distribution. Also, you must determine the exclusive blockers, that is, symbols that are themselves unrestricted, but that do restrict the distribution of others. Those elements that are not free are all on the tier, and also all of the exclusive blockers are on the tier. And that is it. Those are the symbols that are salient. This method only works for tier-based strictly local languages where the factor width is 2. A method that works for wider factors, but is a batch learner, was proposed by Jardine and McMullen in 2017, where first you find the tier by finding all factors of width k-1 through k+1. If inserting a symbol sigma into a k-1 factor gives you a k factor that you haven't encountered, then that symbol isn't freely insertable and must be on the tier. Similarly, if deleting sigma from a k+1 factor gives you a k factor that you haven't encountered, it's not freely deletable and should be on the tier. Also, you have to attend to smaller factors to account for the arbitrariness of whether short words are accepted. But after you've found the tier, you just go back, reread the input, projecting it to only the tier symbols, throwing away all of the non-salient symbols, and learn with any arbitrary KSL learner, which could include the string extension learner that we've already discussed. This is great, but it's a batch learner. It has to reread the input in order to use the SL learner on it. So a method I propose is just using augmented subsequences in a way that accounts for wider factors. For instance, I've placed a couple of English words on this slide, basketball and baseball, that include an SBL subsequence, one of which has A, E, K, and T interveners, and the other just A and E. The constraint gathering phase does restrict itself to only what I refer to as valid augmented subsequences, that is, those where the content of the sequence and the content of the intervener set are disjoint. As you're gathering these augmented subsequences, you only need to maintain the smallest intervener sets. Supersets are implied. So if you see SBL intervened by A and E, that implies that SBL intervened by A, E, K, and T is okay. Now once you've found all of these augmented subsequences for every word in the text, and filtered the results according to the subset principle, a word is accepted if and only if all of its factors, that is, all of these augmented subsequences, is either included explicitly as acceptable or implied by something that's considered acceptable. For instance, we might see tal with no interveners, and you would think, okay, well, by this logic, that would accept the word tail because it has TAL with an I intervener, a superset of the empty set. But if the grammar has AIL intervened only by S, that is, specifically it doesn't contain AIL intervened by empty set, then the AIL with no interveners here is not included or implied by that, and so these would conspire to reject this word tail. In this case, you never actually have to bother learning what the tier of salient symbols is. On the other hand, the structure can be quite large. It is still bounded by a constant, but definitely not small. Now, a problem with this is that a typical tier-based strictly local grammar consists of the tier alphabet, the set of salient symbols, and the strictly local constraints that operate over that tier. Since this doesn't give you the tier, it's perhaps not ideal. But we can return to the method of Jardine and McMullen, collect the local factors of width up to k plus 1, and check for free insertability and free deletability. If you run both of these learners in parallel, then you get all of the information needed to determine acceptance via the augmented subsequences and the set of salient symbols. You could even go further and turn this into a canonical TSL grammar. Once you have the tier of salient symbols, the strictly local grammar of permitted factors is all of the subsequences that consist only of tier symbols, whose set of valid interveners is disjoint with the set of tier symbols, will be permitted factors on the projection. One can simplify this structure, though, noticing that the characteristic sample for determining the tier is all attested factors of width up to k plus 1. We see that this includes all of those factors over the tier alphabet itself. So that's really all that we need. There are some issues with this, though. The characteristic sample is unrealistic. For the Jardine-McMullen tier finding approach, you do have to find every factor of width up to k plus 1, especially those that are over only tier symbols. If you have any kind of constraint intervening on your data, you're not going to see those, and the assumed tier will be incorrect. So I refer to this as the SL-based learner, because it's just reinterpretation of an SL k+1 grammar as a TSL k grammar. But this SL-based learner is broken by basically any other SL constraints or SP constraints that interact with it, because those other constraints will adjust the free insertability or free deletability of things, causing certain symbols to appear salient when they shouldn't. They're salient for the pattern as a whole, but not for the specific tier-based strictly local constraint you might be trying to learn. The augmented subsequence-based learning differs. It doesn't find the tier, but also when confronted with data that isn't pulled from a tier-based strictly local set, it doesn't necessarily guarantee that the result is a tier-based strictly local language. This contrasts with the SL and SP string extension learners, which always return an SL or SP superset of the target grammar. So one thing that I would like to do in the future is continue thinking about ways to improve the robustness of the learning here. That is, ensuring that results make sense and are correct even when there are systematic deficiencies in the data, things missing that should be there. And that's what I'd like to end with. Thank you.